Hey guys, I thought this section had a few complicated ideas that you read about yesterday, but I thought a little explanation might be helpful for you. You're welcome to try to write this stuff down. Otherwise, it's more, I think, me explaining it to you that's going to be the most helpful, and of course you can always go back and look at this video again. So this is section 28.1. It's all about the formation of the solar system and some key ideas about how we talk about the solar system. So where does our solar system come from? So you know our solar system is our sun, which is a star, and all the planets that go around it and their moons and all that other stuff. Well, it started out as a big ball of gas. Okay, let me show you the picture out of your textbook. That kind of is one that still exists in the world. This is on page 796. So this is somewhere where there's this big ball of gas we can see with telescopes. That glares pretty bad. Let me pick this up. And right now, there are new solar systems forming in this blob of gas. And each one of those bright spots is a star. And each one of those stars might end up with planets around it. Okay, they don't always end up with planets, but some of that gas might become planets. So how do we go from a big ball of gas to a bunch of planets and things orbiting a star? Well, all the time, everything that's made of mass is attracted to everything else. And that is by the force of gravity. Okay, so gravity is a force that pulls all things toward each other. So if gas is made of atoms, it's made of little particles. So if you give them enough time, even though that gravitational force is pretty small, they're going to kind of collect and go towards each other. And if you give them many years, those tiny particles are going to collect into bigger and bigger pieces, and they're going to start spinning. Okay, and I put here like an ice skater to remind myself to talk about this. I know figure skating maybe isn't that cool to watch, but I like to watch it. And if you ever watch figure skating, sometimes if there's an ice skater, one of their tricks they do is they spin really fast, right? So they start spinning slow, just a little bit of spin, like it's not even like they're spinning very fast. And then to get going fast, they pull all their arms and legs in tight, okay? And it's kind of the same idea with the planets. So once they start spinning, it's because they're starting to get closer and tighter together. And it's the same physics with the ice skater. So as they pull themselves close to each other, to themselves, they start spinning faster and faster. And it's the same idea with our planets as they form. When those particles start to get really big, like planet size, but not quite yet a planet, we call them planetesimals. I better spell it right. Yeah. Okay, so planetesimal is kind of a word for like a baby planet. Okay. And as they continue to condense and they continue to pick up more and more matter from gravity, they can form two kinds of planets based on what kinds of atoms they are forming from. So if they're forming from big atoms, they'll probably become a solid planet, and if they're formed from smaller atoms, they'll become a not solid planet. But we call solid planets terrestrial. Okay, so like Earth is a terrestrial planet. We have a solid ground underneath of us. And then we have planets like Jupiter and Saturn that we call gas giants. Okay, so if I went to go stand on Jupiter, I would have a hard time. Okay, I would just fall through all the way to the center because there's no solid surface. All right, second half here. Okay, so people used to think everything revolved around us on Earth. They said, well, it looks like the sun goes up and down, and so it must be going around us. And if you went outside at night and you watched the stars for a few hours, you would see that they move too. They go around They look like they go up and then down. And so they thought Earth was in the middle. And another way people refer to rocks and Earth is with geo, like geology we talked about. And so this was the geocentric model, like center. Okay, so we thought the center was geo, that's Earth and rocks, right? So we thought we were in the middle of the solar system. And then astronomy started to grow and people started watching things with their telescopes more. And they especially like to watch Mars and Venus through their telescopes. Okay? And unlike the stars and the sun that continually always rise in the east and set in the west, it seemed like the planets, like Mars and Venus, would go forward and then they would go backwards for a little bit, and then they would go forwards for a little bit. So think about this. You know, if you're standing in the middle of a circle of other people, and the people are going around you, they're going in a circle, they're going to always look like they're going the same direction, right? They're going around you. Okay, now imagine you are outside the circle, and somebody else is in the middle of a circle of people, and people are going around that person. Okay, so if you're watching these people go in a circle, so here's me, okay, and here's, now the people are just dots here, okay, but all the people, they're going this way around the circle, okay, make my arrows a little better. Okay, so from my perspective, I'm looking at it this way. They look like they're going this way, and then they're going the opposite way. Okay, so this would only happen where it looks like they go one way and then the other if they're revolving around something else. Okay, from this guy's perspective, they're always going around, around, around. But from my perspective out here, they're going to the left and then they'd be going to the right. And this is called retrograde motion. Okay, if you've ever heard something called retro, it's probably talking about that it's old. You could say it's from way back, right? So if you're dressed in retro, maybe you're wearing stuff from like the 70s or 80s, right? So it's from way back. It's from before. So that's the idea, is they went forward and then they went back. So retro kind of means towards the back. And so again, this would only be seen, this would only make sense if they're orbiting something else, and we figured out that something else is the sun. Okay, so this proved that the planets orbit the sun, and so instead of reality being geocentric, where Earth is in the middle, we now have the idea that the sun is in the centric, and we call it the heliocentric model. Okay, helio is for sun, and then again, centric is that it's in the middle. Alright, we just have a little bit left here. Planet's orbit shape is not a perfect circle. Okay, so it is not like the sun's in the middle and we're going in perfect circles around the sun. It's actually a shape called an ellipse. It's a lot of time described as egg-shaped. Okay, so here I really exaggerated this one. But the idea is if this was the sun, okay, so the orbit is this elliptical shape around it. And the sun's not in the middle. Okay, so it's actually that our planet Earth is actually further away from the sun parts of the year and closer at other parts of the year. But again, remember from our conversation about seasons, that's not what causes the seasons. Okay, if this was Earth, our winter here in the northern hemisphere, when it's cold, is actually when we're closer to the sun, because it's about the tilt of the Earth rather than the hours of sunshine. All right. I've got one more blank here, and then I want to go back and talk about gravity just a tiny bit more. So miles are too small to measure distances in space, because we'd be talking about just some crazy number of miles. Okay, so instead of miles or even kilometers, we're going to make a new unit that's really, really big. And so they did. They call it the astronomical unit. Okay, or AU. And this is the distance that Earth is on average from the sun. We can say how far Earth is from the sun without saying the on average part, because remember, the distance from Earth to the sun is changing throughout the year a little bit. So we picked the average distance Earth is from the sun, and we called it 1 astronomical unit. And just to give you an idea here, 1 astronomical unit is equal to, make sure I get the number one right, 1.496 times 10 to the 8th kilometers. So that's like 1, 2, 3, 4, 5, 6, 7, 8 kilometers. So almost 150 million kilometers. So it's a really, really, really large unit. All right, so last thing I want to do, because I almost forgot, is talk about gravity just a little bit more. Okay. And I had you watch a whole series of videos about gravity, so hopefully you know the answer to this question. So gravity is the strongest when things are massive and close. Right? So we are pulled to the Earth because it's all both very, very massive and it's close to us. Okay, but if mass was the only thing, then we would all be being pulled to the sun right now because it's the most massive thing in the solar system. But we're not being pulled to the sun because it's not very close. Okay, so its gravitational pull has shrunk because it's so far away. Okay, so it's a combination of these two things. If some things are very massive and very close, gravity is really strong. As the mass goes down, gravity gets weaker. As they get further apart, gravity would get weaker. And if two things are not very massive and very far apart, that gravity is going to be extremely small. So hopefully this video helped clear up some of those ideas from the reading yesterday. As always, let me know if you have any questions. Thanks, bye.